Welcome to section 11.17, part 1. This is the 121st session of the CISSP exam prep series. In this session, we'll map the building blocks of a secure network. We'll answer several questions. How do private network zones differ from one another? What sits in the buffer between the public and the private? Which way does traffic actually flow? How do you keep hardware reliable? What do the core devices do? And how do collision and broadcast domains fit? And how does network access control keep unwanted machines out? Why does this matter beyond the exam? Because you cannot secure what you cannot picture. Imagine inheriting a sprawling campus network with no diagram, just a room full of blinking boxes, until you know which zone is trusted, which device splits traffic, and where outsiders are allowed in. Every control you add is a guess. Getting fluent in these components lets you design deliberately, avoid single points of failure, and place your defenses where they actually count. How do private network zones differ from one another? Chiefly by who is allowed in. An intranet is a fully private network that hosts internal services like web pages, email, and file access for your own people only. An extranet is a carved-out section that behaves like an intranet internally, but also serves specific outsiders. Think chosen partners, suppliers, or a remote sales force. The dividing line is the audience. One is strictly internal, the other deliberately opens a controlled slice to trusted external parties. Picture an office building where most floors are staff only, but one conference floor is set aside for visiting business partners. What sits in the buffer between the public and the private? A screened subnet. It is a special purpose zone built for low trust and unknown users, like the public reaching a web server without letting them touch your internal network. You can build it with two firewalls, one facing the internet and one facing the intranet, so the subnet sits sandwiched and screened between them. Or you can use a single, multi-home firewall with three interfaces, one to the internet, one to the subnet, and one to the intranet. Either way, it is a controlled reception area. Think of a hotel lobby where anyone may enter, but a second set of locked doors guards the guest floors beyond. How does a screened host differ from that subnet? It is a single, hardened system placed just inside a network segment, acting as a gatekeeper. All inbound traffic routes to it first, and it serves as a proxy for the trusted systems behind it, filtering what comes in and hiding the identity of the internal machines. Where the screened subnet is a whole zone, the screened host is one choke point doing the guarding. Picture a single reception desk that every visitor must clear before anyone in the building will take their message. Which way does traffic actually flow inside your network? In two directions worth naming. East-west traffic is the flow that stays within a network, data center, or cloud environment, moving between internal systems side to side. North-south traffic is the flow crossing the boundary, coming in from or going out to external systems. Knowing which is which shapes where you inspect and segment. Picture a warehouse where forklifts shuttle goods between aisles all day, that is east-west, while the loading docks handling trucks arriving and leaving are north-south. How do you keep the physical hardware reliable? By planning for power, warranty, and support. Reliable power is foundational. So beyond surge protection and battery backup, consider redundant power supplies. A common design has two supplies, each carrying half the load. So if one fails, the other instantly shoulders the full demand, and some even allow hot swapping without downtime. Beyond power, always ask about warranty and return terms when you buy, so a failed device can be refunded or replaced. And confirm what technical support is available, since advanced gear may demand vendor expertise you do not have in-house. Think of buying a delivery van. You check not just the engine, but the spare tyre and the service plan. What do the core network devices do, and how are they layered? They map neatly onto the lower layers of the reference model. At the lowest layer sit signal boosters, repeaters, concentrators, and amplifiers, plus the hub, which is really just a multi-port repeater. One layer up work bridges and switches, which move frames by hardware address, with switches able to carve out separate segments. At the next layer up sit routers, steering traffic by logical address between networks. A helpful anchor is that the lower the device, the dumber and more broadcast prone it is, while higher devices make smarter, more targeted decisions. Picture a mail system where a simple loudspeaker shouts to everyone, a sorting clerk hands mail to the right desk, and a regional dispatcher routes between whole buildings. Why do collision and broadcast domains matter here? because the device you choose decides how chatter spreads. A collision happens when two systems transmit at once on a shared path, and the collision domain is the group of systems that could clash that way. Any device at the second layer or higher splits a collision domain. A broadcast is one system reaching all others, and the broadcast domain is everyone who hears that shout. It takes a third layer device to divide a broadcast domain. So the smarter the device, the more it contains the noise. Picture a crowded room. A low partition stops people from bumping into each other, but only a solid wall stops a shout from carrying across. What other specialized nodes round out a network? A handful of purpose-built helpers. A jump server is a hardened waypoint you connect through to reach a sensitive system more safely, common in screen subnets and cloud networks, and it should only ever accept encrypted connections. A sensor gathers information and ships it back to a central system for analysis. A collector is any system that quietly records specific activity into a log, and an aggregator pulls many inputs together into one stream for processing. Many of these run on a system on a chip, a tiny integrated computer that packs a processor, memory, and networking onto a single chip, powerful but often too minimal for rich security features. Picture a security office where guards feed observations to one desk that logs, combines, and forwards them upward. How does network access control keep unwanted machines out? By enforcing your security policy automatically at the point of connection. Its job is to check that every device joining the network is patched, compliant, and authorized, and to keep the rest out. It can act before admission, demanding a device meet requirements before it may communicate, or after admission, judging access by ongoing user activity. It can run through an agent installed on each system, or agentlessly by scanning from a central server. Non-compliant machines can be quarantined to a remediation area until they are fixed. Think of a doorman who not only checks your invitation but also confirms your vaccination card before letting you into the party. So let's bring it together. Intranets serve your own people. Extranets open a controlled slice to trusted outsiders. And a screened subnet buffers the public from the private, while a screened host does the same job as a single choke point. Traffic flows east-west, inside, and north-south across the boundary. Keep hardware reliable with redundant power, warranties, and support. Know your devices by layer, from dumb repeaters and hubs up to smart routers. And remember which devices split collision versus broadcast domains. Add specialized nodes like jump servers and sensors, and let network access control gate every machine at the door. In the next part, we dig into firewalls and proxies. The MCQs covering all the topics and concepts from this session are available on rucloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.